Here I have the hyperbola x squared over 9 squared plus y squared over 5 squared, minus y squared over 5 squared equals 1. It has vertices at 9, 0 and minus 9, 0. And the distance between the two vertices happens to be 18. The foci, one of them is here at 10, 0, and another one is over here at minus 10, 0. Now, if I take some other points on the hyperbola, like this point over here, and I measure this distance, and I measure this distance, and I subtract those two things, I end up getting 18, which happens to also equal the distance between the two vertices. And it's a property of a hyperbola that no matter where I pick a point on the hyperbola, if I take the distance to each focus and I subtract those two numbers and I take the absolute value of that, I'm always going to get the same number, and that number is always going to be the distance between the two foci, the distance between the two vertices, and that's something that I'll prove in a later video, but for now that's a definition. If it's on this branch, well, this distance is going to be smaller than this distance, but the absolute value of the difference is, so we can say this: absolute value of PF1 minus PF2 is equal to 2a. And that's an important property of hyperbolas. Will be proved in another video, but for now, let's just say it's a thing. Once you know that there is some kind of magic distance, actually, why don't I say constant for now? I want to show you why that constant has to be the distance between the two vertices. The reason why is, if I take a point like right here, the actual vertex, and call that P, which is at 9, 0, notice how PF1 is PF1 is this distance and PF2 is this distance. Well, if I subtract PF1 minus PF2, see this PF2 is also equal to, let's just call this guy Q, it's also equal to QF1. So if I think of it that way, when I subtract this green line minus this red piece, which is the same as this red piece over here, what I'm left with is the thing in the middle. In other words, the constant is actually equal to 2a, and it's not an accident that that happened. Now, once we have the property that any point on the hyperbola, the difference between the two distances is a constant, I can make hyperbolas with this concentric circle graph paper. So here I have this point A, and notice how point A is compared to point F2. It's on the it's on the third circle out, but compared to F1, it's on the 1, 2, 3, 4th circle out. So AF1 minus AF2 absolute value equals 1. 4 minus 3 is 1. Well, if I look for other points, there are other points that are 4 away from F1 and 3 away from F1, 3 away from F2 and 4 away from F1, namely over here. That's 1, 2, 3 away, and 1, 2, 3, 4 away. While I'm at it, I could have points that are 3 away from F1 while being 4 away from F2, so I have these 4 points. That's just for doing 4 minus 3. But there's other numbers that have a difference of 1. For instance, 3 minus 2. So if I go 2 circles away from F2, I'm on this circle, and 3 circles away from F1, I'm on this circle, so I get a point here that's 2 away from one and 3 away from the other. And here's another point, that one's 2 away from F1 and 3 away from F2. But there are other points also, like this point over here is 4 away from F2, 5 away from F1. This is 5 away from F2, 6 away from F1. And in doing so, finding all the points whose common difference is 1, I get the two branches of a hyperbola. This hyperbola has a pretty high eccentricity. We can see since the foci are 5 units apart, 1, 2, 3, 4, 5, C is 2.5, our center is somewhere over there, and A is actually 0.5, because the center of the hyperbola is on the midpoint of the line connecting the two vertices. So E is equal to 2.5 over 0.5, which is 5. So this has pretty high eccentricity. The final thing we did on this day was we did a paper folding experiment where we had a circle and a center point, and we picked some kind of point over here which we call P. And if you pick a point anywhere on the circle and you fold R onto P, you get a perpendicular bisector. And then if you connect R to O and maybe sort of keep it going until it intersects the fold you just made and call that point S, that point S is going to end up on a branch of a hyperbola. And the reason why that is O and P would be the two vertices. I'm sorry. O and P would be the two foci. Now, SP minus SO. Well, SP, because of the way the fold was made, S is on the perpendicular bisector of R and P, so SP is also the same as SR. But SR minus SO is actually OR, which is just the radius. So no matter where I pick it, at least on this branch, it's going to end up having that common difference is going to be the radius of the circle, and that's why it makes a hyperbola.